9.1 Quadratic graphs and their properties. Standard form of a quadratic. Y equals ax squared plus bx plus c. Here are a few examples of quadratics. Y equals 3x squared, y equals x squared plus 9, y equals x squared minus x minus 2. The quadratic parent function is y equals x squared or f of x equals x squared. And we learned previously that y and f of x basically represent the same thing. Now let's look at the graph of a quadratic. The graph of a quadratic is a shape called a parabola. The parabola can open upward or downward and is somewhat of a U-type shape. The point that is its highest or lowest, depending whether it's opening upward or downward, is called the vertex. The axis of symmetry is a line that goes through the vertex. And if you remember back to what symmetry means that it's a line that cuts something in half and would be the same on both sides, like a mirror image. So that's the axis of symmetry. In this case, it happens to be the y-axis, but that is not always the case. If the a value is greater than 0 in y equals ax squared plus bx plus c, that tells us that the parabola opens upward, as in the picture above, and the vertex is the minimum point, the lowest point on the parabola. If the a value is less than 0, meaning it is a negative number, then that's when the parabola opens downward and the vertex is the maximum point, which is the highest point on the parabola. Now we're going to identify a vertex. What are the coordinates of the vertex of each graph? Is it a minimum or maximum? So let's look at graph 1. The vertex in graph 1 would be 0, 1. And that would be the maximum point, because as we stated previously, when it opens downward, your vertex is going to be your maximum point, the highest point. And you could see in this graph that the point 0, 1 is the highest point on the graph. In graph 2, the vertex would be 0, negative 1, which would be the minimum point. So when you look at these two graphs, you should be able to tell what that first coefficient, the a term, would be as far as being positive or negative. So in number 1, it's opening downward, so that means that coefficient of the x squared term would be negative. And in number 2, it's opening upward, so the coefficient of the x squared term would be positive. We're going to graph quadratics, and we're going to start with graphing y equals ax squared. So there's no bx and no c, just the ax squared. So our first quadratic is y equals 1/3 x squared, and we want to find the domain and range. We choose the x values that we want to substitute in for x to find y. I'm going to choose multiples of 3 since we're dealing with 1/3 x squared. Then I don't have to worry about having fractions. So I'm going to choose 0, 3, and 6. So when I substitute 0 in for x squared, I just get 0. When I substitute 3 in for x squared, I get 1/3 times 9, which is 3. When I substitute 6 in for x squared, I get 1/3 times 6 squared, which gives me 12. Next, we will plot these points on the coordinate plane. So we have the point 0, 0, we have 3, 3, and we have 6, 12. Now remember, a quadratic is going to make a shape of a parabola, so we have to have that U shape. So since we just have the ax squared term, our vertex will always be at 0, 0. That will change in a little bit, but for now it will always be at 0, 0. So when we go to graph this parabola, we want to make sure that we reflect over the y-axis. So for example, this point 3, 3 also has to reflect over to negative 3, 3. And our point 6, 12 has to reflect over to negative 6, 12. Because for this particular problem, our axis of symmetry is the y-axis. That's our axis of symmetry, so that's what we reflect over. Now we can draw our parabola. And we need to find the domain and range. The domain is going to be all real numbers. Remembering that our domain is our x values. So if you look at our graph, we can pick any x value and we will be able to find a y value. Our graph, even though we only have it up to 6 and negative 6 on the x-axis, the U shape still continues to spread outward if you were going to continue the graph. So it would be all real numbers. Our range is our y values. So if we look at our y values here, we can see that our range is only going to be when y is greater than or equal to 0. You're not going to have any negatives in this graph. Now we're going to graph y equals ax squared plus c. So now we are missing that just the middle term bx. So we're going to graph two quadratics. We're going to graph y equals 2x squared plus 3, and we're going to graph y equals 2x squared, just so we can compare and see that they're different. You're not going to normally put two graphs on one graph. This is just for you to be able to see the relationship between these two types of graphs. So let's start with y equals 2x squared plus 3. So for our x values, I'm going to choose negative 2, negative 1, 0, 1, and 2. So we substitute negative 2 in for x. So we have 2 times negative 2 squared plus 3, and that gives us 11. We have 2 times negative 1 squared plus 3. That gives us 5. 2 times 0 squared plus 3 gives us 3. 2 times 1 squared plus 3 gives us 5. And 2 times 2 squared plus 3 gives us 11. And you see here that whether it's negative 2 or 2, you still get 11. Whether it's negative 1 or 1, you still get 5. And that's because of that axis of symmetry. So we're going to plot these points on the coordinate plane. We have negative 2, 11. We have negative 1, 5, 0, 3, 1, 5, and 2, 11. So we didn't have to reflect anything here because we ended up with both pairs. Okay, so now let's just do 2x squared. Y equals 2x squared. We're going to do that. Now realizing that these are similar quadratics, the difference is the first one we added 3 and now we're not. So we're going to choose the same values for x, negative 2, negative 1, 0, 1, and 2. So I'm going to substitute negative 2. So I have 2 times negative 2 squared. That gives me 8. 2 times negative 1 squared is 2. 2 times 0 squared is 0. 2 times 1 squared is 2. And 2 times 2 squared is 8. Again, noticing whether we have negative 2 or positive 2, they both equal 8. Negative 1 or positive 1, they both equal 2. So negative 2, 8. Negative 1, 2. 0, 0. 1, 2. And 2, 8. Now the question was, how are they different? Okay, and they're different because the graphs are the same shape and same size, but y equals 2x squared plus 3 is shifted 3 units up. So that shows you the relationship between the way these quadratics are written. Y equals 2x squared plus 3 is the same thing as y equals 2x squared, except it shifts it up 3. So when you add 3, it shifts it up. If we were going to subtract 3, it would shift it down. Comparing widths of parabolas, we're talking about how wide or narrow the parabola is. Use the absolute value of A to compare widths. The smaller the absolute value of A is, the wider the graph. The larger the absolute value of A is, the more narrow the graph. So that sometimes confuses people. Smaller is going to be wider, and larger is going to be more narrow. So we're going to order these equations from widest to narrowest. So we're talking about the absolute values. And we're looking for the absolute values of the A terms. So let's look at the first. F of x equals negative 4x squared. So that absolute value is 4. F of x equals 1/4 x squared. The absolute value of that is 1/4. And the last one, f of x equals x squared. Remember that that has that invisible 1, the coefficient of 1, and the absolute value of that would be 1. Now we need to list them from widest to narrowest. Now remember, the widest is actually going to be the least absolute value. So our least absolute value is 1/4. So our widest is going to be f of x equals 1/4 x squared. So if we were going to draw these graphs, that would be the parabola that had the widest opening. Then we would have f of x equals x squared. And the most narrow would be f of x equals negative 4x squared. So the trickiest part to that is that you have to get used to the fact that the widest is actually the smallest absolute value and the narrowest is actually the largest absolute value. Have a great night and see you tomorrow.